If you are familiar with any particle in the world, you will see that it's not a perfect sphere. So we must consider the different shapes of the particles. The next chapter introduces how this can be done in the context of discrete element method simulations.
Welcome to this first part of the non-spherical particles unit. As always, we will start with the question what you will learn. First, I would like to go into the implications arising from non-spherical particle shape. You will see that there are multiple implications that require our attention. You will see that orientation tracking of the particles is necessary, and for that we typically use quaternions. So we will talk a little bit about this word. Also, we have a number of shape representation options. We're going to talk about multisphere, superquadratics, and a little bit about spherocylinders. Finally, we will round up this unit by calculation detail, the moment of inertia tensor. The goal is here that you are able to calculate this tensor by hand for simple shaped non-spherical particles. Let us now start with real-world examples. You have seen it already in the teaser for this MOOC. We have grains, particles that are flexible and non-spherical. Also in real-life applications like mining or food industry, we have always non-spherical particles. We focus here in this part of the MOOC on rigid non-spherical particles. So they deform only very slightly at the contact points but have no macroscopic huge deformation. This is important because, as you will see, the moment of inertia tensor for each particle is assumed to be constant. The popular shape models, I have already talked about this a bit, are the so-called multisphere approach, the spherocylinder approach or spherosymplices approach, and the superquadratics approach. You will also see some images from a polyhedra shape approach that we have no time to go into details. Let us now have a look at the plurality of implications that arise if we allow for a non-spherical particle shape. The first group of these implications is related to models and the physics. First, it's easy to understand that the torque can now also arise from a normal contact force, as shown here, and no frictional force is needed to induce particle rotation. Also, fluid particle drag becomes orientation sensitive, so we must be much more careful when picking closures in this field. Most obvious, we need to track the orientation of the particles. Of course, we have to note here that in the classical spherical DEM approach, we only track tangential overlaps. Orientation of the spherical particles is not tracked. More on this later. Also, we need to know the moment of inertia tensor of each particle, so there is a certain amount of pre-processing necessary, and this inertia tensor must be calculated in a particle fixed coordinate system, as it would be natural for any one of us. This particle fixed coordinate system is different from the inertial or global coordinate system that has here subscript in. In contrast, the particle fixed coordinate system has no subscript. We will keep this notation throughout this unit of the MOOC. Let us now have a look at the implications of this global versus particle fixed rotating reference frame. This leads us to the so-called Euler equations that we will discuss later one more time. However, let's look at the equations that we have written down in the very early part of the MOOC. This is the balance equation of the angular momentum in the system. It's important here that this angular momentum L and this moment of inertia tensor in, as well as the angular velocity, is all defined in the global coordinate system. We have not used the indices before because for a spherical DEM-based simulations we don't need these indexes. You see that the main problem is that here this moment of inertia tensor is in this time derivative. The Problem is specifically that this moment of inertia tensor in the global system is time variant, so it changes with time. In short, we cannot directly evaluate this equation. So what we do is we transform all of our important variables, let it be the torque, the angular velocity, and of course the moment of inertia tensor, to the particle fixed coordinate system. In this system, you will see later, we can then solve this equation and obtain our new angular velocities. Please also note that this rotation matrix can be relatively easily calculated from the quaternions, as you will see later. Of course, we can also go back from this representation to the global coordinate system representation, and it's quite easy because we just have to multiply with the inverse of this rotation matrix. Next, let us have a look at the implication for the numerics. As you might imagine, the contact detection between spheres is relatively primitive. We can simply compare the distance between the centers of the spheres with the sum of the radii. For non-spherical particles, this is much more involved, as you will see. Also, the overlap calculation becomes much more tricky, so we have to invest a little bit on the numerical side. As already announced, the solution of Newton's equation of rotation motion is more involved. By the way, that of the translational motion, fortunately, is not changed, so that's the good news. We're going to use quaternions. We must do the mapping of the torque to the particle fixed coordinate system. And finally, if we want to know the angular velocity also in the global coordinate system, we must do this back mapping to the global coordinate system. This is it already for this first part. I hope you enjoyed it. See you next time.